Have you ever really thought about what goes on behind the screen of your favorite app? Well, there's this invisible war being fought constantly just to make that software work, to keep it from crashing, and to make it a little bit better every day. So, let's pull back the curtain on this fascinating world of system control and quality assurance. You know the feeling, right? We have all been there. You're right in the middle of typing a message or beating a level, and then poof, it's gone. The app just vanishes, and you're just staring at your home screen, totally frustrated. Why does this still happen? I mean, even with software from the biggest companies on Earth? It's a fantastic question, and the answer really gets to the very heart of how all software is made. And this is really the fundamental truth we have to start with. This quote from Professor Ujjwal Kumar Pradhan just nails it. The simple, maybe even uncomfortable truth is that perfect software is impossible. It's a myth. Errors are going to happen. So the real magic isn't in avoiding them entirely, but in how we manage that fact. So here's the game plan for this explainer. First, we're going to dig into why all software fails to begin with. Then we'll see how developers try to build practically unbreakable systems, how they plan for the absolute worst-case scenario, and the real art of hunting down flaws. And we'll wrap it all up with the most surprising part, the never-ending story of software maintenance. All right, first up, why all software fails. Let's get right to the bottom of what causes all of our digital headaches. Now, you might think the problems start with a typo in the code, but you'd be wrong. The real origins of error often start way before that, with people just talking to each other. It can be a simple miscommunication, what a user says they want and what a designer hears. Then, trying to translate that human idea into the cold, hard logic of code, that's incredibly difficult. And if the original plan has gaps, which it almost always does, the programmer has to fill them in, basically making educated guesses. And every guess is a potential bug waiting to happen. So if errors are basically a fact of life, how do we even begin to fight back? Well, that brings us to our next section, building unbreakable systems. This is all about being proactive and designing for durability right from the very start. The first big goal is reliability, and I want you to pay close attention to this definition. It doesn't say perfect. It says the system doesn't produce dangerous or costly failures when used in a reasonable manner. It's a built-in admission that things won't always be perfect, but the system should be robust enough to handle normal use without causing a catastrophe. And the second goal, which is just as important, is maintainability. This is all about playing the long game, because a piece of software isn't done when it's launched, it's just getting started. A well-designed system makes it easy to go in later to fix bugs, add new features, and just generally keep it running smoothly. Without this, a tiny fix can turn into an absolute coding nightmare. So how do you get both reliability and maintainability? Well, here's the secret sauce. You don't build software like a giant sculpture carved from one piece of stone. Instead, you build it out of small, independent, focused parts. Think of it like building with Lego bricks. Each brick does one thing and does it well, and you can swap them out without wrecking the whole castle. And this right here shows you exactly what I mean. On the left, you've got the dream scenario, loose coupling. Each part of the system minds its own business and only talks to the other parts when absolutely necessary. Change one piece, and the others don't even notice. But on the right, that's tight coupling. That is a developer's worst nightmare. It's a tangled mess, like a plate of spaghetti, where every piece is connected to every other piece. You touch one thing over here, and suddenly everything over there breaks. It's a recipe for disaster. Okay, so you've designed it beautifully with loose coupling, but things can still go wrong. And that brings us to part 3, planning for the worst. This is all about looking reality square in the eye and admitting that failure is always an option. So there are basically 3 lines of defense. The first is error avoidance. You do everything you can upfront, planning, designing, communicating, to stop errors from ever being created. Then there's error detection and correction, where the system itself is smart enough to spot a problem as it's happening and fix it, or at least stop it from causing a crash. But the final and most robust approach is error tolerance. This is what true resilience is all about. It's not about never failing. It's about being able to take a punch and keep going. Think of it like an airplane that can lose an engine but still fly safely. The system is designed so that even if one part breaks down completely, the whole thing doesn't come crashing down with it. It might be wounded, but it's still functional. And you see this in some of the most high-stakes systems imaginable. For their spacecraft, NASA uses multiple computers all running in parallel. They all do the same calculation, and then they literally vote on the right answer. So if one computer has a glitch, it gets outvoted and the mission is safe. Or think about a power grid during a heat wave. To prevent a total system collapse, the control system might intentionally cause a brownout in one neighborhood. It's not ideal for sure, but it's a whole lot better than a citywide blackout. That's error tolerance in action. Okay, so we've designed a resilient system. Now what? Now we have to actively try to break it. Welcome to Section 4, the art of finding faults. And let me tell you, this is where a lot of people get the wrong idea. Testing isn't about proving your software works. This quote just flips the whole script. The real goal of a tester isn't to get a pat on the back and say, yep, it's perfect. A successful test is a test that finds a bug. A tester's job is to be the bad guy, to be creative in their destruction, to push the program to its limits and beyond with the single-minded goal of making it fail, because every failure they find is one that you, the user, won't have to. And there are two main philosophies for how to do this. On the left is code testing, or what's called white box testing. This is like popping the hood on a car and checking every single wire, every single connection. It's incredibly thorough, but in a huge complex system, it's almost impossible to check everything. On the right, you have specification testing, or black box testing. Here, we don't care how the engine works. We just get in, turn the key, and ask, does the car go forward? Do the brakes work? We're testing if it does what it's supposed to do, which is often way more effective at finding the kinds of bugs real people will actually run into. All right, so we've designed it, we've built it, we've tried our best to break it, and it's finally out in the world. We're done, right? Ha, not even close. Let's get to our final section, and honestly, the most shocking part of this whole process, the never-ending story of maintenance. Just look at that number for a second, 60 to 90%. That means that for every dollar spent on a piece of software, up to 90 cents of it is spent after it's released. Building the software is just the tip of the iceberg. The real cost, the colossal hidden expense, is in keeping it alive and well for years to come. So what are we even spending all that money on? Well, this chart is super revealing because it's not what you think. Only about 20% of maintenance is corrective, actually fixing bugs. A whopping 60% is perfective. That's adding new features that users ask for, making things run faster, and generally improving the system. And the last 20% is adaptive, which means updating the software to work on a new phone or a new operating system. So how on earth do you control these massive, ongoing costs? Well, this is where it all comes full circle. The best way to reduce maintenance costs tomorrow is to do things right today. It all goes back to the very beginning, accurately understanding what users want, writing things down clearly, using good design principles like that loose coupling we talked about. It's the hard work you put in up front that pays off, big time, down the road. Which leaves us with this one last really interesting question to chew on. We know perfection is a fantasy. We know that once a piece of software is released, it needs constant attention for the rest of its life. So in this world of endless updates and unavoidable flaws, what does it actually mean for an app to be good enough? That's the tightrope that every single developer, and really every one of us, walks every single day.